In mathematics, a topos is a category that behaves like the category of sheaves of sets on a topological space. Topoi behave much like the category of sets and possess a notion of localization. They are in a sense a generalization of point set topology. The graph-endic topoi find applications in algebraic geometry. The more general elementary topoi are used in logic. Graph-endic topoi. Since the introduction of sheaves into mathematics in the 1940s, a major theme has been to study a space by studying sheaves on a space. The idea was expounded by Alexander Graph-endic by introducing the notion of a topos. The main utility of this notion is in the abundance of situations in mathematics where topological heuristics are very effective but an honest topological space is lacking. It is sometimes possible to find a topos formalizing the heuristic. An important example of this programmatic idea to date is the êtoʊpɔs topos of a scheme. Equivalent definitions. Let C be a category. A theorem of Giraud states that the following are equivalent. There is a small category D and an inclusion C' that admits a finite limit preserving left adjoint. C is the category of sheaves on a graph-endic site. C satisfies Girard's axioms below. A category with these properties is called a topos. Here Pratt denotes the category of contravariant functors from D to the category of sets. Such a contravariant functor is frequently called a presheaf. Girard's axioms for a category C are: C has a small set of generators, and admits all small colimits. Furthermore, colimits commute with fiber products. Sums in C are disjoint. In other words, the fiber product of X and Y over their sum is the initial object in C. All equivalence relations in C are effective. The last axiom needs the most explanation. If X is an object of C, and equivalence relation R on X is a map Rx times X in C such that for any object Y in C, the induced map HOM times HOM gives an ordinary equivalence relation on the set HOM. Since C has colimits, we may form the co-equalizer of the two maps Rx. Call this X, R. The equivalence relation is effective if the canonical map is an isomorphism. Examples. Girard's theorem already gives sheaves on sites as a complete list of examples. Note, however, that non-equivalent sites often give rise to equivalent topoi. As indicated in the introduction, sheaves on ordinary topological spaces motivate many of the basic definitions and results of topos theory. The category of sets is an important special case. It plays the role of a point in topos theory. Indeed, a set may be thought of as a sheaf on a point. More exotic examples, and the raison d'être of topos theory, come from algebraic geometry. To a scheme and even a stack one may associate an êtoʊpɔs topos, an FPPF topos, a Nesnevich topos. Counterexamples. Topos theory is, in some sense, a generalization of classical point set topology. One should therefore expect to see old and new instances of pathological behavior. For instance, there is an example due to Pierre Deligne of a non-trivial topos that has no points. Geometric morphisms. If X and Y are topoi, a geometric morphism U, X, Y is a pair of adjoint functors such that U preserves finite limits. Note that U automatically preserves colimits by virtue of having a right adjoint. By Freyd's adjoint functor theorem, to give a geometric morphism XY is to give a functor U, YX that preserves finite limits and all small colimits. Thus geometric morphisms between topoi may be seen as analogues of maps of locales. If X and Y are topological spaces and U is a continuous map between them, then the pullback and push-forward operations on sheaves yield a geometric morphism between the associated topoi. Points of topoi. A point of a topos X is defined as a geometric morphism from the topos of sets to X. If X is an ordinary space and X is a point of X, then the functor that takes a sheaf F to its stalk Fx has a right adjoint. So an ordinary point of X also determines a topos theoretic point. These may be constructed as the pullback push forward along the continuous map X. 1x. Essential geometric morphisms. A geometric morphism is essential if U has a further left adjoint U, or equivalently if U preserves not only finite but all small limits. Ring Topoi. A ring Topos is a pair, where X is a topos and R is a commutative ring object in X. Most of the constructions of ringed spaces go through for ring Topoi. The category of R module objects in X is an abelian category with enough injectives. A more useful abelian category is the subcategory of quasi-coherent R modules. These are R modules that admit a presentation. Another important class of ringed topoi, besides ringed spaces, are the êtailed topoi of Deligne-Mumford stacks. Homotopy theory of topoi. Michael Arden and Barry Mazur associated to the site underlying a ʻtoʊpɔs a pro-simplicial set. Using this inverse system of simplicial sets, one may sometimes associate to a homotopian variant in classical topology an inverse system of invariants in Topos theory. The study of the pro-simplicial set associated to the êtailed topos of a scheme is called êtailed homotopy theory. In good cases, this pro-simplicial set is pro-finite. Elementary Topoi Introduction. A traditional axiomatic foundation of mathematics is set theory, in which all mathematical objects are ultimately represented by sets. More recent work in category theory allows this foundation to be generalized using topoi. Each topos completely defines its own mathematical framework. The category of sets forms a familiar topos, and working within this topos is equivalent to using traditional set-theoretic mathematics. But one could instead choose to work with many alternative topoi. A standard formulation of the axiom "a choice makes sense in any topos, and there are topoi in which it is invalid." Constructivists will be interested to work in a topos without the law of excluded middle. If symmetry under a particular group G is of importance, one can use the topos consisting of all G sets. It is also possible to encode an algebraic theory, such as the theory of groups, as a topos, in the form of a classifying topos. The individual models of the theory, i.e., the groups in our example, then correspond to functors from the encoding topos to the category of sets that respect the topos structure. Formal definition. When used for foundational work, a topos will be defined axiomatically. Set theory is then treated as a special case of topos theory. Building from category theory, there are multiple equivalent definitions of a topos. The following has the virtue of being concise. A topos is a category that has the following two properties. All limits taken over finite index categories exist. Every object has a power object. This plays the role of the power set in set theory. Formally, a power object of an object is a pair with which classifies relations, in the following sense. First, note that for every object, a morphism induces a subobject. Formally, this is defined by pulling back along. The universal property of a power object is that every relation arises in this way, giving a bijective correspondence between relations and morphisms. From finite limits and power objects, one can derive that all colimits taken over finite index categories exist. The category has a subobject classifier. The category is Cartesian closed. In some applications, the role of the subobject classifier is pivotal, whereas power objects are not. Thus some definitions reverse the roles of what is defined and what is derived. Logical functors. A logical functor is a functor between toposes which preserves finite limits and power objects. Logical functors preserve the structures that toposes have. In particular, they preserve finite colimits, subobject classifiers, and exponential objects. Explanation. A topos as defined above can be understood as a Cartesian closed category for which the notion of subobject of an object has an elementary or first-order definition. This notion, as a natural categorical abstraction of the notions of subset of a set, subgroup of a group, and more generally subalgebra of any algebraic structure, predates the notion of topos. It is definable in any category, not just topoi, in second-order language, i.e., in terms of classes of morphisms instead of individual morphisms, as follows. Given two monics m, n from respectively y and z to x, we say that mn when there exists a morphism p, y, z for which np equals m, inducing a preorder on monics to x. When mn and nn we say that m and n are equivalent. The subobjects of x are the resulting equivalence classes of the monics to it. In a topos, subobject becomes, at least implicitly, a first-order notion, as follows. As noted above, a topos is a category C having all finite limits and hence in particular the empty limit or final object 1. It is then natural to treat morphisms of the form x, 1x as elements xx. Morphisms f, x, y thus correspond to functions mapping each element xx to the element fxy, with application realized by composition. One might then think to define a subobject of x as an equivalence class of monics m, x, x having the same image or range, mx, xx. The catch is that two or more morphisms may correspond to the same function, that is, we cannot assume that C is concrete in the sense that the functor C set is faithful. For example, the category grph of graphs and their associated homomorphisms is a topos whose final object 1 is the graph with one vertex and one edge, but is not concrete because the elements 1g of a graph G correspond only to the self-loops and not the other edges, nor the vertices without self-loops. Whereas the second-order definition makes G and its set of self-loops distinct subobjects a G. This image-based one does not. This can be addressed for the graph example and related examples via the Yonnet dilemma as described in the examples section below. But this then ceases to be first-order. Topoi provide a more abstract, general, and first-order solution. As noted above, a topos C has a subobject classifier omega, namely an object of C with an element T omega, the generic subobject of C, having the property that every monic m, x, x arises as a pullback of the generic subobject along a unique morphism f, x omega, as per figure 1. Now the pullback of a monic is a monic, and all elements including T are monics since there is only one morphism to one from any given object, whence the pullback of T along f, x omega is a monic. The monics to x are therefore in bijection with the pullbacks of T along morphisms from x to omega. The latter morphisms partition the monics into equivalence classes each determined by a morphism f, x omega, the characteristic morphism of that class, which we take to be the subobject of x characterized or named by f. All this applies to any topos, whether or not concrete. In the concrete case, namely C faithful, for example the category of sets, the situation reduces to the familiar behavior of functions. Here the monics m, x, x are exactly the injections from x to x, and those with a given image mx, xx constitute the subobject of x corresponding to the morphism f, x omega for which f-1 is that image. The monics of a subobject will in general have many domains, all of which however will be in bijection with each other. To summarize, this first-order notion of subobject classifier implicitly defines for a topos the same equivalence relation on monics to x as had previously been defined explicitly by the second-order notion of subobject for any category. The notion of equivalence relation on a class of morphisms is itself intrinsically second-order, which the definition of topos neatly sidesteps by explicitly defining only the notion of subobject classifier omega, leaving the notion of subobject of x as an implicit consequence characterized by its associated morphism f, x omega. Further examples: every Grothendieck topos is an elementary topos, but the converse is not true. The categories of finite sets, of finite G-sets, and of finite graphs are elementary topoi which are not Grothendieck topoi. If C is a small category, then the functor category SETC is a topos. For instance, the category graph of graphs of the kind permitting multiple directed edges between two vertices is a topos. A graph consists of two sets, an edge set and a vertex set, and two functions s, t between those sets, assigning to every edge e its source s and target t. Graph is thus equivalent to the functor category setc, where C is the category with two objects C and V and two morphisms S, T, EV giving respectively the source and target of each edge. The Vaughan dilemma asserts that cop embeds in setc as a full subcategory. In the graph example, the embedding represents cop as the subcategory of setc whose two objects are V as the one-vertex no-edge graph and E as the two-vertex one-edge graph, and whose two non-identity morphisms are the two graph homomorphisms from V to E. The natural transformations from V to an arbitrary graph G constitute the vertices of G, while those from E to G constitute its edges. Although setc, which we can identify with graph, is not made concrete by either V or E alone, the functor U graph set two sending objects G to the pair of sets graph and morphism H gh to the pair of functions graph is faithful. That is, a morphism of graphs can be understood as a pair of functions, one mapping the vertices and the other the edges, with application still realized as composition but now with multiple sorts of generalized elements. This shows that the traditional concept of a concrete category as one whose objects have an underlying set can be generalized to cater for a wider range of topoi by allowing an object to have multiple underlying sets, that is, to be multi-sorted.